Okay, 2011B. Answer the following questions about the solubility and reactions of the ionic compounds MOH2 and MCO3, where M represents an unidentified metal. Identify the charge on the M ion in the above compound. Okay, obviously, oops, I hate when I do that. So what happens is, that the hydroxide ion has a -1 charge, and you should know that the carbonate ion has a -2 charge, and so in either one of these, it just makes sense that the charge is +2, because the reason you need two hydroxides is 2 times -1 is -2 plus 2, and then if CO3 is -2, then M would have to be +2. Pretty easy question. That's just a one-pointer. Calculate the molar concentration of the OH minus in the saturated solution. Interestingly, MOH2, sorry, that's bad writing, is a base. Arrhenius said that acids dissociate to make H plus ions in solution. Bases dissociate to make OH minus in solution. So the question is, if the pH is 9.15, which is obviously basic because pH is defined as if the pH is greater than 7, it's basic, or a synonym for that is alkaline. You don't see that too much, but you do hear it a little bit, especially with the alkali metals and the alkaline earth metals. If the pH is less than 7, it's acidic. Acidic. Okay, now if the pH is 9.15, then the POH is 14. And remember, this is exact, 14.00000 minus 9.15. And so what happens is the POH then has to be 4.85. Remember, this is 14 exact. So this has infinitely many decimal points. This has 2, you get 2. But now the question is, and remember now, POH is the negative log of the hydroxide ion concentration. And so if you know this is 4.85 and you're looking for this, let's call this X just so that it matches your math class. The first thing you would do to solve this equation is to divide both sides by -1. And so you end up with -4.85 equals the log base 10 of x. What's the only thing in all of math that undoes a log base 10? An exponential base 10. And so you end up with that x is 10 to the -4.85. Maybe last year you learned the formula this way. OH minus is always 10 to the negative POH. So we know that the POH is 4.85, -4. And anyways, and remember, sig figs are weird on pH because only the numbers after the decimal point count. And so X comes out to be, which again is defined as this, 1.4 times 10 to the -5 molar. So right here, this is the answer for B. Or sorry, I. We're on BI, and then we have BII. What is the solubility constant expression? So the thing is, you have to write down, well, MOH. Now, because they asked for KSP, because solubility product means KSP, that means this stuff isn't very soluble, and it dissociates into M plus 2. That's the reason we did A, plus 2 OH minus. And so the KSP would be, remember, pure liquids and pure solids don't filter in or factor in. It would be the concentration of the metal ion with the +2 charge times the concentration of the hydroxide ion, but because this 2 goes up here. So this is the answer for II. And calculate the value of KSP. Well, KSP is, we know from I is that the concentration of OH minus is 1.4 times 10 to the -5. That was the answer for And we know that the KSP is the concentration of plus. So what happens is, this is interesting, if you look up here, this is a 1 to 2 mole ratio. That means this has to be twice as much as this. And so the next thing we need to do is figure out that the M plus 2 ion concentration is 1.4 times 10 to the negative 5 divided by 2. Because 1 to 2, this concentration has to be twice as much as this. And so then that concentration ends up being, if you do 1.4 times 10 to the negative 5 divided by 2, you end up with exactly 7.0 times 10 to the negative 6 molar. And then using this equation up here, so what do I put in for M plus 2? 7.0 times 10 to the negative 6. What do I put in for OH? 1.4 times 10 to the negative 5, but the formula says you have to square that. And if you put that in your calculator and you round to the appropriate number of sig figs, you end up with, believe it or not, 1.4 times 10 to the negative 10th. That's very tiny. Okay, that does not seem right to me. Let me just do that. I don't think it's 10. I think it might be 15. Sorry. I can't read my own writing. Let me just pause. I'm not sure. Let me just do this on my calculator while we're waiting. It's really bad when your teacher can't read her own writing. 7.0 second EE negative 6 times 1.4 second EE negative 5, but I have to square that bad boy. And I end up with, that's what my calculator says, 1.372 times 10 to the negative 15th. But this has 2 sig figs and this has 2 sig figs. And so that's where I got the 1.4. And then times 10 to the negative 15, not negative 10. That was a bad mistake. That's a tiny number. All right, next thing. For metallic carbonate, the value of the KSP is 7.4 times 10 to the negative 14th. On the basis of this information and your results in part B, which compound, MOH2 or MCO3, has the greater molar solubility in water at 25 degrees? Justify your answer with the calculation. Okay, so this is crazy, and this is the one thing I remember my college professor just hammering on this. You cannot just look and say, oh, negative 15 is bigger than or smaller than negative 14. Because what happens is, let me just do the M. I'm going to do the MOH2 first. Okay, so this dissociates like this. M plus 2 plus 2OH minus. And now I'm going to do my ice chart. And this, I can't even tell you how important that you understand this. This solids, but negative S is solubility. Because what this equation means, this side, the left side, is the undissolved side. The right side is the dissolved side. And so what happens is this is 0, this is 0, this is S, this is 2S. And so 0 plus S is 2S, and 0 plus 2S is 2S. But we actually know that 2S is 1.4 times 10 to the negative 5 molar. And if that's what 2S is, then S is 7.0 times 10 to the negative 6 molar. Now, why this is important is right here. S, the reason we use S's and not X's like everyone else, S stands for solubility. It means how much of this solid stuff goes away because it dissolves. And the way that you decide is which one is more soluble is the one that has not the biggest KSP value, but the one that has the biggest S. Now, what happens is we have to do the same thing for the other one and then compare the answers. So what happens is this MCO3, this dissociates, remember this is a solid, because we only do KSPs on slightly soluble ionic compounds. This dissociates not in a 1:2 ratio, but a 1:1 ratio. And then when I do my ice charts, ICE, M, 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 and we we don't really do solids in the calculation, but what we call this negative S, because when this stuff dissolves, the solid goes away and it converts over into solid. So, into dissolved species. And so this is a 1:1:1 mole ratio. So this and both of this goes down, and then 1:1:1, and then 0 plus S is S, and 0 plus S is S. And so now we know that the KSP value would be the concentration of M plus 2 times the concentration of CO3 minus 2. And, sorry, minus 2 goes in there. And then they told us up here, got to slide up here again, that this was 7.4 times 10 to the negative 14. And so what we know now is, well, this is 7.4 times 10 to the negative 14, and our table defined this as S, and this is S. So 7.4 times 10 to the negative 14 equals S squared. What undoes a square root. And if you do this, S comes out to be, S stands for solubility, 2.7 times 10 to the negative 7 molar. And so what we have here, I'm going to switch colors. God, I hate it when I bump that thing. Sorry. You can obviously see that 2.7 times 10 to the negative 7 molar is a smaller number than 7.0 times 10 to the negative 6 molar, because negative 7 is a smaller number. And so the question was, I got to go back and read the question. Which has the greater molar solubility? Justify your answer with the calculation. I don't know that you actually needed to do this calculation right here. What did I do with that? Oh, this is crazy. Did I just delete something? Hold on. Undo. Let me do undo. Yes, I don't know that you needed to do this one, but anyways, which one has the greater molar solubility is MOH2 has the greater molar solubility. And justify your answer with the calculation. This is the calculation you did. And then you can move on. And then the very last question is, MCO3 decomposes at high temperatures to this. If you guys remember your reaction rate stuff, and you might not, metallic carbonates when heated decompose into metallic oxides plus carbon dioxide. When I teach this, I always go, just think of carbonated beverages give off carbon dioxide gas. And so then the question is, a sample of MCO3 is placed into a previously evacuated container, heated to 423 K and allowed to come to equilibrium. Some solid MCO3 remains in the container. What is the value of Kp? Well, interesting. Kp only applies to pressure. This cancels, so Kp is equal to the pressure of the carbon dioxide gas, and this is a 1, so this is a 1. Okay, determine the pressure of the carbon dioxide gas in atmospheres. Well, they told you right here that the pressure was 0.0012. Kp is 0.0012, and that's equal to the pressure of the carbon dioxide. So the pressure of the carbon dioxide must be 0.0012 atmospheres. Holy mackerel, it doesn't get any easier than that one. And then indicate whether the value delta G for the reaction is positive, negative, or 0. Justify your answer. God, that looks weird. I don't know why. Sorry. You learned delta G naught. Girls are not real tough when they're having kids naturally. Well, R is 8.31 joules per mole K. It might actually be 8.314. I guess I don't remember right now how many sig figs they keep. This is 423 K. And then we have the ln of 0.0012. And if you put that all in your calculator, and by the way, this in the old test you didn't get a calculator on these questions, but on the new test you do. So if you do negative 8.31 times 423 times the ln of 0.0012, the answer comes out to be 2364, sorry, and I don't care about 2364 joules, or if you prefer 23, sorry, I only get two sig figs, 24 kilojoules, but it's positive 24. So what is the answer? Positive. They don't even want to know the answer, they just want to know positive. The other way you could do this without a calculator is this is positive, this is positive. When you take the natural log of a number less than 1, it's negative. For instance, the log base 10 of 0.1 is negative 1. The log base 10 of 100th is negative 2. If you're trying to take the log of a number between 0 and 1, it's negative. So this is negative, this is negative, a negative and a negative is a positive. But the answer to the question is positive.